Hi guys, this lecture video is on the quantum mechanical model of the atom, which is the most powerful and the most current model that being used right now. Now, just like the rest of the other two models, the Rutherford and the Bohr model that we have previously discussed already, then each of the atoms it basically attempts to explain and help us understand about the arrangement of the electron surrounding the nucleus of the atoms. Because chemistry is the study of electron, and of the three subatomic particles, it turned out that it is the electron that dictate the chemical property of the atom. So therefore, given any atom, we need to know the location and the energy of each of the electron. And this is basically the heart of the quantum mechanical model that help us understand and be able to predict the location of the electron and how much energy that the electron have. And combining those two together, it helps us understand about the chemical behavior of the atom. And briefly, this is what the quantum mechanical model of the atom would look like. It includes of this spherical shape right here with a lot of dots in them. And we'll go over what's the meaning to these dots in a little bit. And here are the summarizing key points of the quantum mechanical model. First, it is impossible to determine the exact location of the electron at any moment of time. So we simply don't know it. And when it comes down to the location of the electron, it's then all about probability. And the dots on the quantum mechanical model that we see here represent a region with high probability that we'll be able to find the electron there. So all of this dot represent region of high probability where we'll be able to find the electron. And this region right here are also known as the orbital. An orbital is basically a region in space outside the nucleus. So here is the nucleus, and outside of it where we'll be able to find the electron. And some of the differences in this quantum mechanical model compared to the Bohr model is as follows. In the Bohr model, Bohr stated the electrons are found in the orbits. And now in the quantum mechanical model, the statements that we now have is as follows. Electrons are most likely to be found in orbital. So the term orbit in the Bohr model are now replaced with the word orbital in the quantum mechanical model. And because it turned out that this statement by Bohr is not correct, we cannot find the electron. But electrons are most likely to be found in the orbital. And the third statement from the quantum mechanical model. So the quantum mechanical model uses 4 quantum numbers to describe the energy of the electron, as well as the probability where those electrons would locate. So there's 4 quantum numbers. And the 4 quantum numbers are as follows. The first quantum number is called the principal quantum number. Now this can also be referred to as the principal shell. So principal shell or principal level. And the second quantum number is called the angular momentum number, and that is abbreviated with this L right here. And this is also called the subshell or sublevel. And the third quantum number is called the magnetic quantum number, and this is abbreviated with ML. And now this represents the orbital. And lastly, the spin quantum number, and this refers to basically the spin of the electron. So there are 4 quantum numbers, and when we know them, then we'll be able to figure out the energy and the probability where we'll be able to find the electron. So in summarizing, this is what this is all saying right here. For every set of electrons, for any electron that we have, every electron in an atom will has a set of these 4 quantum number right here. So every electron in an atom has a set of this 4 quantum number. There will be a value for it N, another value for it L, another value for it ML, and another value for it MS. And when we know all these four numbers right here for electron, we'll be able to figure out the location of the electron in terms of probability. And we'll be able to also figure out the energy, how much energy that this electron would have. And combining these two together, once we know about the location and the energy of electron, we'll be able to understand the chemical property. So chemical behavior or property of the electron and the atom that the electron is found in. So this is why that it's very important that we understand and we learn about this four quantum number. But here in this class, we will not be focusing so much on this, and because this is a topic that we'll dip very deep detail in Chem 400. Now let's now go over more information about the quantum mechanical model to help us understand the four quantum number. So again, it is all about the arrangement of electron outside the nucleus of the atom. That's what the goal of the quantum mechanical model would be. And now, so let's go over this. So first, in the quantum mechanical model, electrons are first organized into principal shell. And the different principal shell then have different energy to them. And this determines the energy of the electron. If the electron were to be found in the first principal shell, it would then have the energy of the first principal shell. And that would then have less energy compared to the electron that locate in the higher principal shell. So for an example, here are the different principal shell. And this different principal shell right here is basically very equivalent to the orbitals that we have seen from the Bohr model. So it basically the different orbits are now replaced with the principal shell. So here are the different principal shell. So the principal shell number 1, this is the one that again closest to the nucleus, and it have lowest energy. So if an electron were to be found in this principal shell, it be the closest to the nucleus and have lower energy, versus an electron were to be found in the 7 orbits or the 7 principal shell. Then now this is the furthest or further from the nucleus, and this will then have higher energy. An electron in the principal shell number 7 will have more energy compared to an electron in the lowest principal shell. And within each of the principal shell, there's one or more subshell that we designate with S, P, D, or F. And the number of subshells and sublevel in each of the principal shell is then equal to the number of the principal cell itself. And each subshell is designated as follows. So here's what happened right here. We have the different principal shell. Let's say here is the nucleus of the atom, and here surround this. These are the different principal shell. So let's say here is the first principal shell, here the second principal shell, here the third principal shell, and here will be the fourth principal shell. So each of this row right here represent a principal shell. On the first principal shell, there's actually one subshell or sublevel. On the second principal shell, there's now 2 subshells. So it further split into 2 subshells or sublevel. On the third principal shell, there's now 3 subshells. And on the fourth principal shell, there's now 4 subshells. So the number of subshells within each of the principal shell is then equal to the principal number itself. And we can further designate to each of this subshell right here as follow. First, so this one right here would be first the number of the principal shell that it locate in, followed by S. And this one right here, there's 2 subshells, and they designate as 2S and 2P. On the third principal shell, there are 3 subshells, and they designate as 3S, 3P, and 3D. And on the fourth principal shell, there are 4 subshells, and they've been labeled or designated as 4s, 4p, 4d, and 4f. So those are the number of subshells that are found in each of the principal shell and how we would designate to them. Now within each of the subshell, there can be one or more orbitals in different orientation, and each types of orbital have different shape to them, and the shape of the orbital is then determined by the type of subshell that this is in. So what this means as follows: each of this subshell right here can be further split into different number of orbital. For the S subshell, there's only one orbital. But now for the P subshell, the P subshell is further split into 3 orbitals. And this is the reason why that when we have the 1s, we do not split this into any other orbital. And same thing with the 2s subshell over here. Now moving on to this 2p above here that we have seen. So we now this further split into 3 orbital. So that's what we see right here. So each of this area in here represent an orbital. And similarly, the D subshell consists of 5 orbitals, and we can call them 5d orbitals or 3p orbital and so on. So here an example right here. So on the third principal shell here will be the 3d subshell, and this 3d subshell right here is further split into this 5 different areas representing the 5d orbitals. And lastly, the F subshell. So the F subshell consists of 7 F orbitals. So those are the number of orbitals that go into each of the subshell. And these are the shapes of the different orbitals right here. If we were to have the S orbital, or orbitals, they come from the S subshell, and we also call them the S orbital. Its shape would then be spherical, and this is what it would be. And so this is the dot representation of it versus this is the shape representation of it, but it's spherical. So this dot right here represents the area where we will be able to find the electron if the electron were to locate in the S subshell or S orbital. In this space, this is where we'll be able to find its electron. And here will be the shapes of the p orbital. So let's write this. So this is spherical versus p orbitals. P orbitals are basically orbitals that are part of the p subshell. So we call them p orbital. This basically look like dumbbells. So they look like dumbbell. We call them a dumbbell shape. Or we can also describe this as having 2 balloons that tie together. So this is what each of them would look like. So this is the dots representation, and this is the shape representation. And in here, in this space, that way we'll be able to find the electron if the electron would be found in the p orbital. And now, so the p orbital, there are 3 different orientations to it. So this one right here is on the x orientation, this one right here is on the y orientation, and this one right here is on the z orientation. And going back to this diagram that we have seen over here, this is what this would mean. So 2px means that it is the p orbital on the second principal shell on the x orientation. And this one right here would then be the p orbital on the second subshell that locate on the y orientation, and this one on the z orientation. So going back, the shapes are all similar except they locate on different axis or different orientation. And moving on to the d orbital. So these are the shapes of the different d orbital right here. And when it comes down to the d orbital, these are 5d orbital because the d subshell is further split or consists of 5d orbital in them. And these are the shapes of the 5d orbital. 4 of them look almost the same, except they locate on different orientation. So this is the one on the YZ axis, this one on XY axis, and so on. And this one right here, this last one right here, look uniquely different than the other. But for the most part, we can see this look like having 4 balloons that tie together. So that's the shapes of most of the d orbital. Now, we do not need to be concerned with the labeling of the different d orbital, but then we just have to recognize that the shape look like they have 4 balloons that tie together, and there are 5 of them located on different orientation or different axis. Now, so on this diagram right here, this poster right here is something that I call the atom neighborhood. And this atom neighborhood right here is basically an analogy to actually help us understand about the quantum mechanical model. So we do realize that when it comes down to the quantum mechanical model, it can be very, very complicated, and because we do not teach them in enough detail, because that is not the purpose of this class. And when we don't teach enough detail, it may be very difficult for students to see, to understand and see the whole big picture of it. So this diagram right here is an analogy to actually help us understand about the quantum mechanical model. So here's what it is right here. The analogy as follows. We have this neighborhood that we call the atom neighborhood. And this neighborhood right here is then used to house people. And this is very much similar to an atom housing an electron, because we see that there's many atoms that have a lot of electron in them, right? And now, in a way, they need to be able to house the electron. So the housings of people in this neighborhood is equivalent to the housing of electrons in an atom. And so this diagram right here is being designed in such a way that it perfectly complements to the quantum mechanical model. And so we just have to understand how this layout is and be able to see the connection between this atom neighborhood and this quantum mechanical model, and we'll be able to make association and figure out the terminology. So hopefully this diagram right here will be helpful for many of you. So now let's go over this atom neighborhood right here, how it's been designed. And by learning the design of this atom neighborhood, it helps us understand about the designs of the quantum mechanical model as well. So in this neighborhood right here, we have a manager office, and this is equivalent to the nucleus of the atom. And now there are different streets: first street, second street, third street, and fourth street. And this street right here are basically equivalent to the principal shop. Now on the first street, there's one house. On the second street, there are 2 houses. On the third street, there are 3 houses. And on the fourth street, 4 houses. And on the fifth street, 5 houses, and so on. So there are different streets and different number of houses on the different street. Now on the first street, there's one house, and the house that exists on this first street right here, we're gonna call this the S house. So imagine the S being a types of house model. So in this case right here, on the first street, we have one house, and that is the S house model. Now this S house model right here has only 1 bedroom to it. So, and that's the house that we will find on the first street. On the second street, there are 2 houses. There's one S house, and now there is a newer house model they call the P house. And this P house right here, unlike the S house, it consists of 3 bedrooms in it. Okay, and moving on to the third street. On the third street, there are 3 houses. There is the S house, a P house, and now a new type of house, a D house. And this D house right here consists of 5 bedrooms to it. And on the fourth street, there are 4 houses: an S house, a P house, a D house, and now the F house. And this F house right here consists of 7 bedrooms in it. So that's kind of how the houses would work out. And the value that you see above here, these are basically the renting prices. So the prices to house per person. So that's what that value would be. Now, so how did this relate to the quantum mechanical model right here? Then it goes as follows. The street is equivalent to the principal shop. The house is then equivalent to the sub-shop. And the bedroom is then equivalent to the orbital. Now, ultimately, the people will be living in the bedroom, right? Just like how ultimately the electron will be found in the orbital. And the S house has one bedroom, and that equivalent to saying that the S subshell consists of one orbital. The P house has 3 bedrooms, and that equivalent to saying the P subshell consists of 3 orbitals, and so on. And the renting price of the bedroom is then equal to the energy of the orbital, and people would then equivalent to electron. And the happiness of the people would be the stability of the electron, and happiness of the person is then the stability of the electron, and happy of the neighborhood and happy of the people. So that's kind of how it would work out. And so the principal quantum number is then equivalent to the street number. The angular momentum number is then equivalent to the house model, and then the magnetic quantum number, the bedroom number, and so on. So in this class, we're not going to discuss all of the use of the 4 quantum number, but each of this bedroom right here further would have one value to it, and that is called the magnetic quantum number. But then that is not the emphasis of our class, so we'll ignore that quantum number for now. Okay, so here in this case right here, let's say that we have certain number of people that we need to house. Then our goal is to house people in the cheapest way possible. And so therefore, if we were to have people, we have to put them in the house, the S house on the first street first. And here in this case right here, each of this bedroom right here can accommodate 2 people maximum. So the maximum amount of people you can put in each bedroom would then be 2, and we have to pair them together. So first you will put people in this S house on the first street first, and once this is been filled, then now we move on to the second houses, the houses on the second street. And because the S house here is cheaper than the P house, so therefore the next people you'll be putting them in the house on the S house on the second street, and we'll label this as 2S. So this is labeled as 1S house, and this is labeled 2S house, and this is labeled 2P house, and this is 3S, 3P, 3D, and so on. So we'll be putting them in the 2S house first, and this 2S house consists of, again, only 1 bedroom. Now the P house here consists of 3 bedrooms in them, so technically speaking we can accommodate up to a maximum of 6 people on this P house. Okay, and again 2 people here on this 2S house. So technically speaking, the houses on the second street can accommodate up to 8 people, and that's important right there, because we need to be able to keep track and figure out how many electrons can be accommodated in each of the principal shell. Okay, so this is how this atom neighborhood analogy would go, and I hope that it is helpful for many of you in understanding about the quantum mechanical model. And as we learn about the electron configuration later, this diagram right here, or this poster, will continue to be helpful in allowing us to see the association to the quantum mechanical model. And now, in summary, the quantum mechanical model. So again, it helps us, it shows the arrangement of the electron. An electron are first arranged into the principal shell. And in each of the principal shell, there are different number of subshell, and they're designated as S, P, D, and F. And they have different shape to them of their orbital. And each subshell, they have different number of orbital. The S subshell has 1 orbital, the P subshell have 3 orbital, the D subshell have 5 orbital, and the F subshell have 7 orbital. This is equivalent to saying that the S house has 1 bedroom, the P house have 3, the D have 5, and the F house have 7 bedrooms. And now each orbital can contain 2 electrons maximum in opposite spin. And so this is the last quantum number right here, but we'll care less about this, the spin of the electron for now. And the electron are then filled into the lowest energy orbital first. So this is equivalent to saying that we have to keep house people in the cheapest house first to minimize the cost. And that's exactly what happened in the atom as well. And now let's complete this table right here to help us keep track of the orbitals and the subshell and the designation and so on. Now, so on the first principal shell, so the principal shell number 1, there's one subshell. So this is equivalent to saying there's one house on the first street. And we would designate that subshell as 1S. Or basically how we would label the house on the first street would be, we call that the 1S. And then the number of orbitals that exist in this subshell right here will be 1. And because again, so this is equivalent to saying there's one bedroom in the S house. And because now has only one orbital, the maximum number of electrons they can accommodate will then be 2. And now moving on to the second principal shell. How many subshells would exist in the second principal shell? Then the answer, there will be 2. There is the S house or the S subshell and the P subshell. And we will designate them as 2S and 2P. For the 2S subshell, it has consists or further split into one orbital, versus for the 2P, then the 2P subshell consists of 3 orbitals in them. So when we combine them together, there are 4 orbitals altogether on the second principal shell, and therefore it can accommodate a maximum up to 8 electrons. And moving on to the third principal shell, there are 3 subshells, the S, the P, and now the D, and we would designate them as 3S, 3P, and 3D. And the 3S, it further consists of 1 orbital. The 3P now consists of 3 orbitals, and the 3D now consists of 5 orbitals in it. So combine all of this together, we have 9 orbitals that exist on the third principal shell, and therefore it can accommodate a maximum of up to 18 electrons. And moving on to the fourth principal shell, there are 4 subshells, and they are the 4S, 4P, 4D, and 4F. The 4S consists of 1 orbital, and the 4Ps again will be 3 orbitals. So this is again equivalent to saying there are 3 bedrooms in the P house on the fourth street. And here will be 5, and here will be 7. So when we add all of this together, this equal to 16 orbitals that exist on the fourth principal shell, which can accommodate up to a maximum of 32 electrons. So that's how we can figure out how many subshells, how many orbitals, and how many electrons can each of the principal shell can accommodate. And now, let's now discuss about the energy of the orbitals. So the energy of the orbital is very much equivalent to the renting in prices of the house if we were to refer to that atom neighborhood. So the different orbitals are different in energy, and it's very important that we know how much energy that each of the orbital have, and the patterns, basically the order in energy of the different orbital. Which one have higher orbital, have higher energy than the other. So that pattern is something that we need to be able to figure out. So here in this case right here, when we move on to this quantum mechanical model, we see the prices as follow. This 2S right here is the cheapest, followed by this one, followed by this one, the 200, followed by this one, and then followed by this one, the 300. And now here we have 400. But now this one right here is actually only 350. So the next one is this one, and followed by this one. And then now we go back to this one again. And then we go back to this one. And if we were to basically put in the 5th and the 6th street, then now we'll go back to somewhere above here again, and so on. But it's important that we know the prices in each of this house, so that way when we house people, we can put them into the cheaper house first to minimize the cost. And when it comes down to the atom, it is the same thing. We have this different orbital right here, S, 1S, 2S, 2P, 3S, 3P, 3D, and so on. How are they increasing in terms of energy? So it's important that we figure out the order of energy of the different orbital. And it turned out to be as follows. Depending on what types of atom it is, whether it consists of 1 electron, or multiple electrons, the patterns can be different. And the patterns is then known as the off-ball principle. So here is for the hydrogen atom right here. For the hydrogen atom, which is different than the rest of all other atoms, the energies of the different orbital depend on the principal quantum number n. So therefore, all orbital that in the same principal level would have the same energy to them. So what this is saying is that the 3s, 3p, 3d, all of these different orbitals right here will have same energy to them, because as long as they have the same principal number, they equal in energy. So this means the following: the 1s will be lowest in energy, followed by the 2s and the 2p, and the 2s and the 2p would have same in energy. And now the 3s, 3p, 3d will be same in energy as well. So this is only true for the hydrogen atom. Versus for a multi-type electron atoms, which basically pretty much the rest of all the atoms except for the hydrogen, then this is how the order in energy would be. So the 1s on the first principal shell, we have the 1s, and that is lowest in energy. Follow, now when we move on to the second principal shell, we have the 2s and the 2p, and the 2s is lower than energy than the 2p. And now moving on to the third principal shell, we have the 3s, 3p, and 3d, and the 3s is lower in energy than the 3p and 3d. And now moving on to the fourth street, here is this 4s right here. This 4s right here, it actually have lower energy compared to this 3d. So that's something very important we need to be able to recognize. Okay, so within each of this principal shell, the s will have lower energy than the p, and the p will have lower than energy than the d, and the d then have lower energy than the f. But as we get further to the higher, the more principal shell, then and when we compare the different orbitals from the different principal shell together, then they do not follow that trend anymore. So it's important that we recognize this pattern. So that is the pattern of increasing in energy right there. And we need to remember this pattern right here, so that way we know which one have more or less energy, and we can put the electron into the correct orbital. Now, so there's several ways where we can learn this pattern right here, and it's really important we again recognize this pattern. Now, from hopefully from high school or in some of the textbook, you might have seen of this diagram right here that allow us to figure out this pattern. But here in this class right here, we're not gonna teach you this pattern right here because this is high school chemistry. So here in college, we want you to be able to use the periodic table to be able to figure out this pattern right here. And yes, the periodic table has so much information in it that by using it, it is also possible for us to figure out this pattern as well. And knowing this pattern right here and knowing how to do this and not using this above would also be very helpful as we learn how to do electron configuration. Now, to be able to figure out this pattern right here by using the periodic table, this is what we will do. First, we split the periodic table into 4 different blocks: the S block, the P block, the D block, and the F block. So the first 2 groups are called the S block. And now the group from group 13 to group 12, so these are the transition metal. The transition metal are then called the D block. And the P block would be for the non-metal over here from group 13 to group 18. And the lanthanide and the actinide, these are then the F blocks. So those are the 4 blocks: S, P, D, and F. And now we're going to label each of these blocks right here with a number depending on the period that it exists in. For the S block, so if the element is located on the first row, it now becomes 1s. Versus if it is on the S block and now on the second period, this is now called the 2s, and then 3s, 4s, 5, and so on. So the numbering of each of this row is the same thing at the period number. Moving on to the P block, the numbering of the P block depending on the period that they're in, it is also the same thing as the period number as well. So the same as the period number. Now moving on to the numbering of the D block, the D block is actually one value lower compared to the period number. So here in this case right here, this is the 4th period. But when it comes down to this row right here on this D block, we will label this as 3D. And this one right here, located on the 5th period, but it will be labeled as 4D, and so on. And moving on to the F block, the number of the F block is actually 2 values lower than the period number. So technically speaking, this lengthening right here, this lengthening, this entire row is supposed to be fitted in here. It's supposed to be inserted in here, where we would have seen this lengthening. And here in this case right here, so this row actually located on the 6th period, but when we number this is only 4. And similarly for the octanine is supposed to be inserted in here after this element. So this is where the octanine would be. So technically speaking, the octanine is belonging in the period 7. And now when we number this entire block, it is 5F. So that's how we would number the block. And once we have learned how to number all this already, we can do the following. We can go from left to right, and then top to bottom. And we'll be able to figure out the pattern that we have seen over here. So how this goes as follows. So we're gonna start from the very first. So this is 1S, and we go from left to right. So 1S, going across all the way. And after 1S, we have 2S. And after 2S, we then have 2P, and then 3S, and then 3P, and then 4S, and then 5D, and then 4P, and then 6S, and then 4D, and 5P, and then 7S. Now after this 7S, and we get to this element, we go all the way to this bottom because this is where it's supposed to be inserted in. So 6S, and now 4F. And once this entire row is complete, we go back here again to 5D, and now 6P, and then 7S, and now go down here to the 5F, and then go back here to the 6D and the 7P over here. And that would allow us to perfectly come up with this pattern right here. That is very important for us to recognize in order to do electron configuration.